Hello, I am Ziqi Zhang. I'm currently a postdoctor at the University of Illinois, Urbana-Champaign. I'm happy to present our work, No Privacy Left Outside, on the insecurity of T-shaded DIM partition for on-device ML. This work was done when I was a PhD student at Peking University, China, with my collaborators from Peking University and Hong Kong UST. With the fast development in the last year, LLM is regarded as an expensive and sensitive property. On the one hand, companies spend millions of money to train the LLM. On the other hand, LLM is applied to private tasks, such as medical record and financial data. Thus, the traditional solution that deploying LLM to edge devices faces new security challenges, the sacrifice of the LLM security. Specifically, the possibly malicious device owner can gain the white box access to the LLM. Thus, the attacker can perform membership influence attacks on the training data and model stealing attacks on the model weights. Trusted execution environments, also called TEs, can help to protect model security. The model owners can deploy LLM to the T of user devices. Thus, the device owners can no longer see the internal information of the LLM. The goal of T-based defense is to downgrade the accurate and efficient white box attacks to inaccurate and slow black box attacks. Trusted execution environment is a secure area on the main processor to provide data confidentiality and code integrity. The advantage of T is the high security. T can defend strong adversaries such as OS, but the disadvantage is the limited computation resources. T has only limited memory and lacks GPU support. However, directly deploying the models in the T will introduce large overhead. The challenge comes from the contradiction between the limited computation resources of T and the large amount of computation demand of the LLM. To solve this challenge, researchers propose T-shaded DIM partition (TSDP) solutions. These solutions partition the model into two parts. One part is large but unimportant and privacy irrelevant, and the other part is small but critical and privacy related. The privacy irrelevant part is offloaded to GPU for fast computation, and the privacy related part is shaded by the T for high security. The insight of TSDP is that if we can design a perfect partition by keeping the shaded part small and critical, the offloaded part on GPU will leak almost no privacy, and we can enjoy both low latency and high security at the same time. To summarize existing TSDP solutions, we surveyed 15 papers that were published on top-tier conferences over the past 5 years, as well as papers that were cited by these papers. Except for 5 papers that do not fit the scope, we categorize the other 10 papers into 5 classes. These solutions include shading deep layers, shading shallow layers, shading large magnitude weights, shading middle layers, and shading nonlinear layers. All these solutions use empirical results to evaluate the security. They used surrogate model-based attack and found that the attackers cannot directly use the DIM part on the GPU to perform the attacks. However, we want to ask, does this conclusion hold in the era of LLM? It is because the insight of prior TSDP defense is based on empirical observation. For example, the large magnitude weights are important, but we cannot guarantee the small and medium magnitude weights contain no privacy. Besides, the threat model may change. Prior TSDP may become ineffective against stronger adversaries. To study this problem, we evaluate prior TSDP solutions against the strong adversary who can access the public model and public data to help analyze the defense schemes. Our evaluation includes both model stealing, which evaluated the leakage of model functionality, and membership inference, which evaluated the leakage of training data privacy. We use 2 baselines, black box and white box no shield. Black box means defender put the whole model in the T. This baseline has the lowest utility and highest security. No shield white box means all the model is put on GPU. This baseline has highest utility and lowest security. Here is the attack pipeline. The attacker first uses the offloaded model part and public model to initialize the surrogate model. For the shaded part of the victim model, the attacker uses the same part of the public model to initialize. This initialized model is then used for model stealing to train the surrogate model. The surrogate model is then used for membership inference. Our evaluation includes multiple datasets, model architectures, and metrics. As it is difficult to evaluate all solutions, we select representative solutions from each category. For shading deep layers, we select darknets. For shading shallow layers, we select the SERDAB. For shading large magnitude widths, we select the magnitude paper published on the TSDP. For shading intermediate layers, we select sorter. And for shading nonlinear layers, we select the shadow net. Our first research question is, how is the defense effectiveness of prior TSDP solutions of each category? In this table, we use the accuracy of surrogate model on the target task to evaluate the performance of model stealing. It is because the goal of model stealing is to copy the functionality of the victim model. Thus, a higher accuracy represents the attacker steals more functionality. For membership inference, we use the accuracy of the confidence-based attack. The last average row represents the relative attack performance of each setting compared with black box baseline. Take model stealing as an example. The attack performance of no shade is 4.26 times higher than black box. For darknets, which shades the last few layers in the T to protect the training data privacy, the attack performance is 3.92 times higher than black box. Similarly, for magnitude, the attack performance is 3.91 times higher than black box. We found that the defense is similar to the white box defense. The reason lies in the motivation of the TSDP solutions. T only shades a little width. The majority model part on the GPU still exposes a large amount of privacy. Our second question is, can we improve the TSDP security by simply adjusting the deployment configurations? This problem can be formulated to finding an optimal configuration. The optimal configuration is a config with the lowest utility cost that can satisfy the constraint that the security difference between the configuration and black box is less than the threshold. However, directly solving this formulation is difficult, so we iterate over large different configurations for each TSDP solutions and try to empirically find the honey spot. Here is our results. In the figures, each curve represents a TSDP solution. The x-axis is the shaded flops or shaded computation amount of computation, and the y-axis is the attack success rate. We can observe that each curve extends from the upper left to the lower right, which means the security can only be improved by shading more layers and widths. Besides, the shape of each curve is different across models and datasets, which means the config for each curve to reach the black box security is different. We found that it is difficult to improve the security of TSDP solutions by only changing the configurations. It is because the security utility trade-off exists in all settings. The optimal configuration for different settings are different. It seems that in the era of LLM, we can no longer have the cake and eat it anymore. But is that true? During our study, we found that the fundamental limitation of the existing solution is that they all use the training before partition strategy. During the training phase, all the weights are updated by private data and may contain privacy. Thus, it is difficult to separate the privacy-related weights and irrelevant parts. Based on this observation, we propose to use partition before training strategy. This strategy first separates the privacy-related part and unimportant part before training. Then we use the private training data to only update the private related part. We call this critical part as privacy related model slices. In this way, we can guarantee that except the model slices, other model parts are never updated by private training data and contains no privacy. Based on this insight, we propose T-slice. The goal of T-slice is to compress the functionality of a private model into private slices. The slices can be integrated into a public model and perform the same functionality as the private model. The pipeline of T-slice consists of two steps: dense slice training and slice simplification. The first step integrates multiple slices to the public backbone to ensure model capacity. The second step iteratively prune unimportant slices to reduce the slice size. Here is a comparison between T-slice and other TSDP solutions. The advantage of T-slice is that all weights that are ever updated by private data are shaded by T's, and all weights on GPU are never updated by private data and are privacy irrelevant. We also need to take care of the communication security after deployment, because the internal features may leak the weighting information in the T. To solve this problem, we use one-time pad proposed in Slalom, which is highly secure and efficient. The internal features of DNN are encrypted by the T and then sent to GPU. GPU can compute the results over ciphertext and send the ciphertext back to T. Finally, T can decrypt the results. Experimental results show that T-slice can provide black box level protection with the lowest utility cost. In each figure, the red star at the lower left represents the performance of T-slice. T-slice can reduce the computation cost by a large margin. One possible concern of T-slice is that, does it lead to the performance loss in other aspects? The answer is no. We evaluate possible performance losses on other aspects, and we found that the accuracy drop is only 0.34%, and the exposed backbone does not increase the attack performance as well. We also evaluate the performance on real devices. We use PyTorch and SGX SDK to implement an evaluation framework called TOISM, a T-based confidential heterogeneous framework for DNN models. Experimental results show that compared with black box protection, T-slice can improve the throughput by a large margin. In this paper, we first recap existing TSDP solutions and found that they are not suitable in the era of LLM because the offloaded model part on the GPU exposes a large amount of privacy. The reason of the vulnerability is the training before partition pipeline. From this insight, we propose T-slice that uses partition before training paradigm to isolate privacy and accelerate model inference. We have released our artifact as well as our tool, TOISM. Thanks for listening.